Phil Science Lab, sponsored by ESB's Generation Tomorrow programme, supporting initiatives that help young people develop key skills in science, technology, engineering, arts and maths.
Now, it is indeed Phil's Science Lab, and Phil joins me on the line. You're going to examine density using dancing raisins. Do explain, Phil.
Yeah, I thought we'd kind of do something a little bit different. This is uber simple to get set up. So, I mean, there's no reflection on you, Tommy, over the last few weeks. This is just
all right.
Exactly
No need to get personal.
We're not at all. We're kind of talking about how things are compressed in liquids, and also how, like at that density, how you can cause something to lift up and fall down. And what we're going to do initially is just take a look at the 2-litre bottle that's in front of you, and this is carbonated or sparkling water. So there's carbonation or carbon dioxide pressurized inside this, and what you're going to do initially is just you feel how hard that feels pressurized.
Yeah.
If you try and squeeze that bottle, it's hard.
Yeah.
And this is due to Henry's law. So it's the amount of pressure, the partial pressure of that. You've pressurized carbon dioxide inside it. So once you open that, so you can open it, when you release the pressure, you should see bubbles come up.
Yeah, and that's obviously something we're all familiar. I mean, I'm uber simple, Phil, but not that uber simple. We've all seen that phenomenon before.
Yeah, you've seen it before, but you've never really realised what's happening. So this is carbon dioxide being released by pressure. And all we're going to do is add that to the glass.
Okay.
So what I want you to do is pretty much fill the glass that you have in front of you with this carbonated water. So water that has carbon dioxide that's been pushed into it. And that's sitting there. And what we're going to do now is we're going to take some raisins. Take like 4 or 5 out of them, the ones that you have there. And all I want you to do is to drop them into the glass. And you should see bubbles start forming.
They sink to the bottom?
They do. And what's happening now is they should start...
Look at those dancing raisins. So what's happening here?
It's like that sentence you never thought you'd say. So what's happening here is that the carbon dioxide adheres or sticks to the outside of the raisin. And because carbon dioxide is lighter than the water, it's less dense. Once enough of them attach outside the raisin, they start lifting up and floating up. But when they get up to the top, they burst, and then they...
Phil, I've got some reluctant dancers here. It's like at a wedding, where the uncle doesn't want to leave the bar and hit the dance floor. There's a few of them just stuck at the bottom.
And then they go up and they come back again. But this is really lovely because now the reason why this is happening is because raisins are wrinkly, and on the outside of them there's something called what are nucleation sites. And what there is, they're areas of kind of larger surface area. So like where there's a little dip, so the carbon dioxide bonds there, and that's where the the bubbles of carbon dioxide come from. You also have some popcorn kernels there as well. So you can throw them in and see what happens to them, and hopefully something similar will happen, but potentially on a different time scale.
Will I throw a few in, Phil, yeah? A few of them?
Pardon?
Throw a few in?
Put a few in for a second. And again, 5 or 6, and you'll see them start doing the same thing. Now, the interesting thing about this is when we're working scientifically, you want to compare different things, try different things out, so that's what we're doing with this. The funny thing about raisins is there's a few nucleation sites on it, but there are certain things that have lots and lots of nucleation sites. So you have a Mento, or the white mint sweets there.
Oh, popcorn's going.
Popcorn's going already.
We've got a few. We've got a few popcorns. Yeah.
It's quite fun. You'd spend ages looking at it. Now, but the Mento itself, like a golf ball has lots of dimples on it.
Yeah.
A Mento is like one of them, but it has millions of little dimples on it. If you drop the Mento into the same glass, because it has so many of these sites, you should see it fizz a lot. You should start to see fizz come constantly from it.
I've one really enthusiastic raisin that keeps dancing. Not sure about the rest of them. But yeah, I can see that the fizz coming off the Mento now, Phil.
Yeah, is a lot. So it's because there's so many more nucleation sites, it goes up a bit, and because it's happening and releasing the gas more. So what I thought we'd try and explain is what happens when you kind of increase both the carbonation and also the amount of nucleation sites. So you're up in the ante. So with this is why we have some Coke and why we have some more Mentos.
So that's not something that's actually in the Mentos. It's not because of the sugar or whatever the ingredients in the Mentos. It's because of the surface of the sweet.
No, it's because of the surface. So like a golf ball, you've got these little dimples. So it's like little places. So a nucleation site could be a dimple. It could be a scratch. It could be where something's folded. It's anywhere that carbon dioxide can gather, build up, and then make it float. So that's what's happening here, and why you're seeing the raisins float up.
It's going mad in the glass now, Phil. The popcorn's going in, the Mentos. It's a right party.
Exactly. I mean, but it's also, it's fascinating to watch, and it's great that you can test lots of different things and see what's happening in it. But we're going to try and up the ante now with the Coke. So if you take the Coke bottle that you have in front of you, put it in the middle of the tray, and gently open the bottle itself. Again, you see Henry's Law in action, where the pressure is being released. Now, Coke is a highly carbonated, saturated. When you get saturated from the rain, you're soaked. Yeah. This is soaked in carbon dioxide. So what I'd like you to do is to take 3 Mentos in your hand. I want you to put them kind of in a little tower, as in put them on top of each other. And I want you just, when you're ready, or look at your countdown, is to drop them into the Coke and see what happens. So there's a lot of carbon dioxide, a lot of nucleation sites. You ready?
Yeah.
3, 2, 1, drop it in, and straight away. So all of the carbon dioxide released really quickly. Now, we have a small bottle with a wide opening at the top. What we'd love is if people send in their videos where you have maybe the bigger bottle of Coke, and if you try to make the opening smaller at the top, send in your videos about how high. But again, you're working scientifically, which is what we do on Steam, to compare, contrast, and see how big you can make these Coke explosions go.
Brilliant stuff, Phil, and it didn't even get any on the suit, so no dry cleaning bill for you. Everybody's a winner. Brilliant stuff, Phil, as always. If you've been following our experiment this morning, we want to see your exploding Coke bottles in your videos and pictures. Send them in to irelandam@virginmedia.ie or WhatsApp us on 089 611 111. Right, we'll take a quick break now. See you back here in 3.
Phil's Science Lab, sponsored by ESB's Generation Tomorrow programme. Check out esb.ie/Generation Tomorrow to start discovering.